Let's go ahead and get started. Where we left off on Friday was with, I think, maybe annoyingly complicated example, just understanding what it means to have kind of both structures and pointers to structures in the same program. In some sense, there's no difference at all. The syntax is otherwise the same in terms of how we declare these pointer variables. We just have to be very explicit when we declare the pointer variable that it is a pointer to our particular variable of a type, right? So instead of int star, it's in this case student data star. That's not really a difference, but being aware of that as we build our pointers is important. Likewise, when we do that memory allocation using malloc, realloc, calloc, the other functions we have available, we kind of use that built-in size of operator to do the math for us, to figure out, I want 15 students, I want to allocate 15 total students, and however many bytes that is, the compiler figures that out for me. I don't have to worry about it myself. It's whatever it is. Like, so that if I consequently change how large first name is or last name is, or whether I add a few more quizzes or labs or other things to that data structure, the rest of the code really doesn't have to change. The size of the structure changes, the amount of memory we dynamically allocate winds up changing, but the code itself doesn't change. We got a little hung up with when we have to use the dot operator versus the new arrow operator. The easiest way to think about this is if you're working with a pointer to a structure, you're going to want to use the arrow operator. When you're working with an individual variable of that structured type, you use the dot operator. And that's really it, though. So do I use the dot? Do I use the arrow? Usually the compiler will tell you when you've done it wrong for whatever that's worth. So if you didn't do dot and you did arrow or vice versa, you'll get the squiggly lines because that is such a common kind of mistake we tend to make when working with pointers and structures. But that's how you need to keep it straight, mostly in your head. So if I have an array of students, whether I dynamically allocated them or statically allocated them, and I take students of 7. I use the array syntax, the square bracket syntax, to return back out a single student, then I would use the dot operator. If instead I have a pointer to a student, whether it be part of an array or just an individually dynamically allocated student, and I want to access the quiz or name one or whatnot of that student, I would then use the arrow operator. And again, the arrow operator isn't really meant to be anything different. It's just recognizing the somewhat verbosity or ambiguity of requiring basically 2 operators to access quiz 1. We need both the follow the pointer operator, go in memory where this is located, and then we also need the dot operator to get the individual component out of the structure. Because we need both of those, this is still syntactically completely valid with the parentheses. This is the more appropriate or common way to do it, just recognizing that we're doing both. That's a design decision. You may not agree with it, but that is the approach we take when we want to access a pointer to an array. Similar to our discussion of, a pointer to a structure. Similar to our discussion of arrays, we have this somewhat hand-in-hand kind of challenge to overcome, which is not necessarily a pointer to a structure, but a pointer inside a structure. We played around a little bit with that, but the example was kind of convoluted on Friday. Review the video if you want to take a look at it again. The idea being that you have this concept of pointers and you have this concept of structures. You can have both a pointer to a structure, and then for the same reason you'd want to have one otherwise, you can have a pointer inside the structure, just as a new component in the structure is itself a pointer. One reason we might want to have it even for something as simple as our student data structure that we have here is to overcome the limitation of that max name kind of built-in assumption here, that we assume that everybody's first name is less than 32 characters as well as is their last name here. That's a limitation of our static memory allocation. We have to decide at compile time how big our arrays can possibly be. We motivated it in terms of images of being of dynamic size, but the same could be the case for names as well, which is we don't necessarily know how long someone's name needs to be until we're past that student's name, and until that becomes an input to our program, until someone types in their name, only then do we really know how long that first name, how long that last name needs to be. So that's a perfectly appropriate use case for a pointer inside a structure is to potentially hold an array of data of a dynamically determined size, of a runtime determined size. Otherwise, the syntax with a pointer inside a struct is exactly the same. It's a char star. If we wanted to allocate 50 bytes to store the first name, we would use malloc or something equivalent to that. We would overwrite my student dot first name with the allocated region of memory. So if you have a pointer within a struct, don't overthink it. It's just an element inside that structure, and you have to do whatever else you'd have to do with pointers for that element inside that structure. The gotcha, though, or the potential gotcha, is this concept of when I copy one variable to another variable, at least in the C programming language, by design, by default, those copies are what's referred to as shallow copies. If I had a student data 1 and I had a student data 2, and I copied and I said student data 2 equals student data 1. How we've been using that this semester is it works exactly as we would hope. Takes all the stuff in student data 1 and copies it over to student data 2. If there's 20 components in this structure, it copies all 20 things over from one variable to another. It's a very powerful way to copy a lot of data over in just one line of code, right? What it would copy if it were the array case, if it were this example, would be every byte within those arrays. It would copy every byte in first name over, it would copy every byte in last name over. It takes all the bytes and just does a pure mem copy from one structure to another. If instead we had just a pointer or pointers inside the structure, when we would do that copy, it would copy just the pointer itself. It would copy the address that is stored inside that pointer, and not the memory itself that's being pointed to by that address. That's why it's referred to as a shallow copy. It copies what's there, but it doesn't copy what's being pointed to by what's there. Sometimes that's what you want. A lot of the time, it's not what you want when you copy one structure to another, because if I want to go from student 1 to student 2, I may in fact want to have a copy of the name and not just point to the same location in memory where that name is found. Depends on what your application needs to do, but if you would like to make sure that the actual memory that's being pointed to by first name and last name are itself copied over to a new variable of that same structure type, you as the programmer are responsible for doing that. You'd have to write your own so-called deep copy functions that would go through, copy not just the things that are part of the structure, but also copy what's being pointed to by any pointers inside that structure. For now, let's assume that's not going to come for too many of our examples this semester, but be aware of that. In a sense, it's correct, right? I'm copying a char star over for first name, and I'm copying a char star over for last name. What is a pointer? It is a variable that stores an address in memory. I'm copying that variable over. I'm copying over the value of that address, but I'm not in any way, shape, or form copying over a block of memory that's being pointed to by that address. If I want to do that automatically, I'd have to use static memory allocation. Or conversely, I'd have to write my own code to follow all the pointers, copy that block of memory over, do my own new dynamic memory allocation for that purpose. But structures and dynamic memory allocation allow us to do a lot more flexible things with our data types and our array type variables than what just basic static arrays would allow us to do. You can use them to create more advanced so-called data structures than what just a simple array provides for you. One such example would be referred to as a vector. Mathematically, we've sometimes been referring to a vector as an array as a vector, but at least in most programming parlance, vector refers to an array type data structure that can dynamically shrink and grow, that you can do things like push something on the end of it, or pop something off the end of it, or insert a value at some arbitrary location inside of it. It's referred to as an abstract advanced data structure because it allows you to have more direct access to things than just what a static array provides for you. There's nothing new here in terms of defining a custom structure, storing a pointer to the potential values we're interested in, as well as what the potential length of the vector is. But if you start with that and you build up a series of functions that allow you to do things like create a new vector, resize a vector, insert a vector at a location, or remove a value at a location, what you wind up then having is a data structure that's a lot more powerful than just trying to manually manage an array. You could always do the kind of code we're about to write here without having a vector type. The thought is, whether you build your own data structure in C, or you use a library that provides them for you, or you switch to a programming language that provides these data structures as kind of built into the language itself, you'll be a lot more productive as a programmer when you can do things like randomly access a location and remove it from a list or a vector or an array without having to manually do all that memory management yourself. It is extra code to do something we would otherwise be able to do. The thought is you do it once, or somebody else does it once and you use their library. And then you have access to this data structure that is a lot more flexible than what a standard array provides for you. This is a reference on the same website we've been using for some of our C-related references to the C++ standard library for the vector class. And we cannot build something exactly the same as this very easily in C, because the feature we actually don't have easy access to is this concept of a template, in which we are going to create something in C++ where later on we determine what actual data type we want it to be. In C, for the most part, we have to decide, do we want this to be an integer vector or a floating point vector or a vector of structures? In C++, we only have to build one. We build it as a template, and then we declare a variable of a particular type. But otherwise, this built-in data structure is something we can build using pointers in C. So it's a vector, it's like an array, it provides a contiguous sequential storage for the values being pointed to by the name of that variable, and then it has additional functions to allow you to dynamically grow or shrink that vector over time. There are quite a lot of functions provided in the standard template library in C++ for vectors. We certainly don't want to try to support all of them, but things like resizing the vector, which allows us to decide for a vector of a particular type, I'd now like to make it a new longer or shorter type. That's one thing we can implement. We can also implement, I have a few of the examples here, insert, which takes a value and a location in the vector and says, I want that value to be located at that location, and everything else is going to kind of get moved over one to provide the space for that new value that we're being provided here. That's another one we can support. We can also do, call it erase or call it remove, which is at a particular location, get rid of the value that's being stored here. Don't just override it with a 0, but actually remove it from the data type itself. Taken together, and there's a number of these functions we can support, but for reasons that'll be pretty obvious as we start to code it, we're going to limit ourselves to just a few. What you wind up with is with a data structure that you really don't have to worry about the underlying implementation of it. You can just worry about what data do I need to store, in what relative positions, and do I, over time, need to dynamically grow or shrink this particular data structure that we have. So we can have, I just listed it on the slide as well, the following 5 functions that we can work on and build together here. So we can have an int vector create, and that's just the name of a function in C, that would take a length input and create dynamically an array of that length. We can then do a resize that would take that same array or that same vector data type and resize it to new length. Then, just like shown in the C++ version, we could create a function called insert, which will take 2 inputs, the actual value we want to insert and the relative location where we would like to insert it. We can then have a remove function, and whether the remove function returns the value that you removed or just gets rid of it, it doesn't really say here. We could do it either way. That removes the value at a given location. And then just to confirm that what we were doing actually works, we'll want to make a function that actually prints these out. And I said global variables to represent our vector. Normally we would put these in a struct. Let's put these in a struct. That would be the correct way to do it here, which would be we would define our struct, and inside that structure would be a pointer to the actual dynamically sized array. That's what values is here. Type def. So when we do a type def, we can actually follow the struct definition with what we actually want to call our int vector later on in our code, so we don't have to use the struct keyword. We can still use the struct keyword to say struct int vector struct, but when defined with the type def keyword ahead of it, that entire block gets defined to be named this, int vector t. And this is called int vector. Unlike in C++, where we could just declare like a templated type where we decide later what we actually want the variable to be, here we have to be pretty explicit at definition time and say it's going to be a series of integer values we're going to create here, and then also some length information. So as we're going to have this dynamic data structure in our code, we're going to be creating it, resizing it, inserting things, removing things. We have to also then, at some way, shape, or form, keep track of what the current length of that array would be. And then we would have the functions corresponding to it. We can still make this code a little bit less painful for now by declaring a global variable and working with that. That's not necessary, but I think there's enough going on here that we'll declare outside of main. That makes it a global variable, a variable of this type. That's probably not the correct approach. These functions should probably be taking as input a pointer to our vector and modifying that pointer itself. For now, I think we're okay making it a global variable. And if we have time, we choose, and if someone wants me to, we can refactor to instead not use a global variable and to instead pass that vector around all of our different functions. For me, and as I've looked through your code in office hours, it doesn't seem like everyone entirely agrees with me. If I'm told as part of a lab that I have to write 5 functions, I want to start off and I want to create 5 function prototypes and just get started with that. That's kind of a copy paste, although we're going to have to be a little bit careful with the copy paste. Maybe this becomes like a comment, creates an array of length len, and because we're using a global variable, we'll make these void functions. They don't have to return anything. Second function resizes an array of length to be length len, so that would be a void function. I just copied the text for what these functions needed to be, and I'm just making prototypes out of them so that no matter where I wind up putting the definition of that function, be it in another file or just elsewhere in this file, the order in which I declare it doesn't matter. The compiler will be aware that these 5 functions exist. And I guess the last one isn't worthy of a, oh, because I deleted the text. Prints out vals. We have 5 functions that, at least as currently written, will all modify a global vector variable, and we can start with our code, right? We can start with a main that would, it really depends on what we want to do, right? We could read in user input. We can just manually just mess around with our functions. Probably the first one we'll want to write that we'll actually want to call will be int vector create of size, 5. We'll call it. This is still something I know that we're all working on, but I always want you, when you think of a function you have to write in your code, I always want you to think of there's 3 parts to every function. Do we remember what they are? 2 of them are already shown here. What are the 3 parts of every function you write? What's this thing called? Prototype. What's this called? Calling, the usage, calling, whatever. And the third type then, third part is? Prototype and definition, I think, are kind of synonymous. The actual implementation would probably be the right word. Absolutely. And I actually kind of like the order in which we did those in. We've talked about how sometimes we wind up writing functions and we forget to use them, like we forgot to actually call them in our program. as we start to write more and more code, it gets harder to see all of this in one screen. That's kind of the value of having a header file, if nothing else, that, it's a separate file that has all your definitions over here, so you can have them open side by side. You can open the same file side by side as well and do that. But prototype is kind of the contract of what my input-output for the function is going to be. The actual implementation, which we still have to write here. And then the actual usage or calling of that function to test it out, right? And I would think we'll probably need to implement at least the create and the print function to be able to do this. So we have this global vector, and maybe we can open up the file side by side. That's the closest thing we can do. See if it'll let me do that without scrolling. Okay, that's fine then. We have this vector variable of this structure, and I want to update it so that instead of having potentially 0 values in it and potentially a length of 0, we're going to have a length of whatever is passed to this function, and we're going to allocate memory of that many elements. So I've passed 5 to this function, but in the more arbitrary sense, generalized sense, we'll be passing length to this function. How do we allocate len, length, number of integers for that vector? What function do we have to call to dynamically allocate 5 of these values in the vector? Malloc would be the one. You could argue, Malloc is correct answer. You could argue that because we haven't set any of the values, we may want to use that other one that 0 initializes, calloc instead of malloc. It looked like with replit, malloc will do good enough for us as well. So in terms of what, hey, I've told you have to work on this function, you don't really know where to go next. Dynamically allocating of an array of length len, we have to use malloc. And the rest is still, we have to maybe have the documentation for malloc open. I don't have it open right now. We have to kind of remember what it's supposed to do. It takes as input, I think we can go back to an example here. This isn't exactly what we want to have to do, but it's an example of it in use. It takes as input a number of bytes we want to allocate, which usually we're actually providing it kind of a formula, right? Give me 15 of these things. That's the formula we're providing it. And it returns a pointer. It returns an address in memory stored in a variable that we want to update a pointer for. What is the name of the pointer that we want to update for our vector? What is it called? That is the data type. This thing is actually, the variable here is actually already allocated. There's a single vector that we've allocated. Within that vector, there's then going to be a dynamically allocated array. And that one's called values, right? So that's what we want to allocate. Again, as I've shown you a few examples here, do you want to go kind of left to right with your malloc lines of code or right to left? Just remember there's kind of 3 parts to it, right, to your malloc. I need to know what is the pointer I'm overwriting. In this case, it may not have been immediately obvious, but there's vector, which is a single value, a variable of that int vector t type, and it's the pointer inside it I want to update. I want to update that values pointer. Again, that sounds weird, that looks weird. Values is a pointer. It is just meant to store an address. Well, I have a function that returns a pointer, returns an address. First part is recognizing what pointer am I overriding with my malloc call. Second part is making sure that I'm casting the return of malloc to be of that type. What is the type of values? It's not int vector t, although it kind of looks like it. It's just an int pointer. That is a pointer to an integer. So we want to cast it as such. We call malloc. You can think of that as the third type, but really we call malloc, and we pass it a number of bytes. And I think we've kind of agreed that best practice for this is to sort of pass it that formula. I want that many integers, so that's how big it's going to be. Give me that many bytes back out, overwrite that pointer, which is global again. If instead, let's stick with the global variable version of this for now. We can refactor it later, but one thing at a time, I guess. we probably, because this isn't just an array, it's going to be a vector, we also are going to want to update the length, which is this second thing we're storing, which keeps track of what the current length is of the vector. Otherwise, we actually have no way of obviously knowing. We'll take that value that we got as input and say, hey, update my vector's length with whatever's passed to this. And then probably we should print it out. And then I guess we should put something in there, I guess. I don't know. So, right, we don't have a good, we could update it, I don't know. Here now, because we've done that dynamic memory allocation, that pointer vector.values now can also be used, we can also use the array syntax for that. So vector.values is a pointer. We can use the array syntax to get an offset of I from that pointer, and we can initialize it to whatever we want. I don't know, some 2-digit value, just some arbitrary value. And then we can print it out. I copied the prototype to where my implementation is going to be. We've done print functions enough. The question is how nice we want it to look. I mean, I don't know. How about we do like vector of size this is equal to this. Vector.length. Print out the current length to show it's an array of that size. Print out like a closing bracket at the end. And then just do a loop that prints out each value. And print out just each value with a little comma at the end. That's vector.values of I. And then print out the last one separately. So it looks nice. All right, we have enough code now we can actually run it. We've created a vector of size 5, just an arbitrary number. We have just randomly initialized, and since we know maybe it's always going to be 2 digits, let's do, I don't know, always print it out as 2 digits. Randomized it to a value between 0 and 99, and then we're going to print it out. And we're going to lose our nice second window here, but we'll come back to it. And I don't know, there's our code. So far, that's really not anything we couldn't have done with just a statically allocated array, right? So at first glance, this is not terribly new. It's just adding extra abstraction on top of it, where we now have a data type that we've declared that is more than just a dynamically allocated array. It's kind of a dynamically allocated array that also has storage to keep track of what its current length is, and it is eventually going to have a series of functions that gives us that more flexible access to it than just allocating and deallocating things. We can do resizing next. I'm trying to think which one would be the easiest one. They're actually quite similar, these last three. So now this is going to resize the array to length len here. We've got to think about what that would mean in practice. We have a current length called vector.length. We have a new input called len, and depending on the value of len versus the value of vector.length, there's actually a couple different things we may or may not want to do here. Well, let's actually call it. So let's call int vector resize. For now, let's make it larger. I think maybe the larger case is a little bit easier. We had create, which allocates. Basically, it's calling malloc for us. Might be easier if we shrink down our print so we can see both these functions side by side. Now, if we want to update that pointer to point instead to an array of size len and not the initial size of vector.length, what function can we call to dynamically change the amount of memory being pointed to by our pointer? There's only 4 of these dynamic memory allocation functions. Yeah, it's okay if you don't have them memorized. Malloc is the one we just used. There's calloc, which zeroes out the memory. There's free, which it looks like we're not going to use at all here. and then there's reallocate. Realloc the memory. And unfortunately, the syntax is just a little bit annoying, and I gotta remember, realloc takes the pointer as input and then the number of bytes. You can kind of see it here as I start to type it in. I'm not sure what happens when I click this. Yeah, is that helpful for you as a programmer? I don't know. By the way, we could try this explain feature. Wait, how do I get to it here? Let's try it again. I lost it. Okay, somewhere there was an explain feature that popped up that said, explain why my code works or doesn't work. And I thought it was kind of interesting in terms of what it did. If it pops up again, I'll try it. Takes the pointer as input we want to modify and then the new number of bytes. It still returns a pointer that we want to overwrite. In the case we're using it here, we're overwriting the same pointer. That's a pretty common scenario that you call realloc and you kind of overwrite the same pointer you passed as input, but that's not a requirement. You can take the result of that and then have two pointers in your system, one to the older block of memory, one to the newer block of memory. But usually we're wanting to update a pointer, so we would overwrite that pointer. So the left-hand side of that assignment operator would still be vectors.values. And the casting would also still be int star. The main difference now is we also pass vector.values as an input to realloc. That's the pointer we are modifying. And in terms of the size, the number of bytes we're passing it here, it's exactly what it was before. It's len times size of int. Give me that many number of bytes now and reallocate it. Question then becomes, if, oh, and then let's not forget, of course, that we then also have to update length to len. I'll bring in a pillow next time. You'll get a more comfortable nap in during class. The question now becomes, what do we do if we have grown the array versus shrunk the array? If you've made the array shorter, if len, L-E-N, is less than vector.length, you really don't have to do anything. There's no guarantee if the memory actually got moved. It certainly is not necessarily getting deleted, those last few elements, but it should work as expected. Now, if len, L-E-N, is greater than vector.length, if len is greater than vector.length, we've extended the array, we've extended the vector. Initialized to zeros or something. We should do something with that memory. This part's a little tricky. We have to think about where the previous length was, where it is now. So we could first check, is len, only do this if len is greater than vector.length. We've made the array larger. We want to take those new elements that we created and initialize them to zeros. Or we could have randomized it. We initialize it to whatever your initialization function is going to be. So if len is greater than our previous vector length, so the order of these two sets of statements actually matters quite a bit. If I had put this one beforehand, they would be equal, but they will eventually be equal. But for now, vector.length is 5, len is 7. There should be two values we need to initialize to 0. And at what index would those values be? Vector.length is 5. The new length, I'm calling it len, but it's also just short for length, is 7. What values of vector.values, what indices of vector.values should we be setting to 0? It was length 5, and now it's length 7. Another way to think about that are, what are the new indices we've created in this array? Previous indices were 0, 1, 2, 3, 4, because it's of length 5. Now there is a 5 and a 6, and those would be the ones that we'd want to initialize. But we want to kind of write that in a more programmatic way. The new index that was not valid before would be vector.length, the previous length. That index 5 was not a valid index, and it is now because we've made the array longer. We want to go to length len, but not including it. And then we want to update our array. I don't know why that's complaining. I'll figure it out, because I didn't declare the int here. Start only if it's longer. If it's shorter, well, I guess that if statement is kind of unnecessary. As it turns out, if it is shorter, right, if len is like 2 or something, then this for loop wouldn't trigger at all anyway, right? Because we'd initialize I to 5. I is not less than 2, so it would never actually execute the loop. So technically that if statement is not really necessary, but it also doesn't cause us a lot of harm either. As I go from a value of 5 to a value of 7, it's locations 5 and 6 in the array I want to update. If that seems like a little hard to really, grok, let's do 15. As I go from 5 to 15, the new indices will be index 5 through index 14 I'd want to update in my array. Oh, well, and then I should print it again to actually confirm that that worked. Looks reasonably correct. You can start to see that, writing these functions is a pain. So the actual value of having to write the function and then use the functions immediately afterwards is maybe not that apparent. But once those functions are written, boy, now you don't have to worry about any of this stuff at all anymore, right? malloc, realloc, calloc, all that stuff is kind of happening underneath the hood. And what you're left with, global variable notwithstanding, which does kind of make it a little bit uglier than it needs to be, but ignoring the fact that there's a global variable involved in the code, you have a really nice set of functions that just kind of take care of that business for you, of determining, I want an array of size 5. Wait, no, I changed my mind. I now want an array of size 15. And using those structure and a pointer in that structure and dynamic memory allocation, using that pointer inside the structure, we get at least part of the way there. Let's now say we want to insert something at a particular location. That would be called int vector insert. That function takes 2 inputs. So again, I'm going to do the implementation last. Int vector insert, a value, I guess I don't really care what the value is, I don't know, 99. And at a location, the location I think for this code to be sensible has to be valid, although we could check for that. We've resized it to size 15. Let's insert it at location 3, just to provide an arbitrary kind of location that we're going to insert it at. So that's the value we're inserting, and that's the location we're doing that insertion. And then to check that it actually works, we should call print again. Inserts value in the array at location look. Let's actually, we can kind of work backwards on this implementation. We're doing an insertion. We're taking a value, we're inserting into the array, we're shoving everything else beyond it to the side over by 1. We're inserting that value of 99. Location 3, I think we should interpret that as index 3. So what was 0, 1, 2, 3, everything beyond that got moved over 1, and then the new value of 99 goes at location 3. I think another way to phrase that would be, this was 83, 66, 77, 15. It's now going to be 83, 86, 77, 99, 15, 93, and then zeros. And there'll be one longer as well. So if we want to work a little bit backwards with this code, what should we do with the vector.length value by the time we're done with this function? Vector.length, what should happen to it? Say it again? I didn't hear you. Not free it. Length, storing the length information for the vector. Currently it should be 15. What should it be by the time that insert function is done? If it was 15, what should it be now? It should be 16. How do we do that? How do we go from 15 to 16? Sure. At the end, we want to increment our value there, right? At the very end, it should be resized by 1. And in this case, just by incrementing the vector value at the end should probably suffice. We could actually also do that using the function we've already created, right? So we know we're basically resizing this by 1. We can be clever if we so choose. We're resize the vector by 1. Well, we already have a function that resizes the vector, right? What's it called? Int vector resize. And you'd be resizing it by vector.length Gotta be a little careful. You wouldn't want to do plus plus. That would do it twice. Give me one more element. Before I worry about the value and the location, I'm inserting something. I want one more entry in my. And we could try that out. It won't be correct yet because we haven't done anything with 99 or location 3. But when we run it, when we print it the third time, and it's kind of unfortunate it's not fitting on the same length anymore, we've started, we've inserted things. Good start. How would we go about actually inserting a value? How would we do it? Take 3 minutes. Think about it a little bit. It's going to involve copying things over. You could use a memcopy function. That would kind of work. We could just manually do it with a for loop as well. I'm going to insert the value of 99 at location or index 3 here. So instead of the value of 15, it should be 99. 15 and 93 should be moved over, and everything should be moved over one. Take 3 minutes. Chat with the person next to you. Give them a little shake to wake them up if need be. A healthy pat on the back. And see if you can come up with how you would write that part. How you would insert something into that vector, in that values array that we have defined. For me, I think this code's a little bit tricky. We can come back here. Maybe even copying the examples over, or just kind of thinking about it a little bit. I'll leave it as a comment, which would be its values. So values of what was value of location is now that val. What was values of location plus 1 is what was previously values of location. Values of location plus 2 is the values that was at location plus 1. That's my pseudocode, and et cetera, right? Up until the final length, which would be values of length minus 1 would be values of length minus 2, because we've already updated the length here. Pseudocode-wise, that's kind of conceptually what we're doing here. Kind of looks similar to the code we were doing for swapping elements in an array, but it's not quite the same. We're not swapping anything. We're just shifting things over by 1. As I start to think about what that would mean from a for loop perspective, well, whenever you see a pattern, life is pretty good, right? 0, plus 1, plus 2, et cetera. You can kind of see where an I variable would kind of make sense. The issue with this is kind of the same issue we had to watch out for when doing our swapping kind of code, is that the order does really matter. That these things are executed from first line to the next line in a sequential fashion. If we were to implement it this way, it'd be exactly kind of backwards, right? We would overwrite location, and then we would take that new value and update location plus 1, take that value and update location plus 2. We got to kind of do them, even though conceptually what we're saying here I think is valid, we kind of have to do them in exact opposite order. Update the upper level values first. I just swapped the order of all those comments here. I'm going to kind of add a ... for all the other things happening in between here. Update the things at the end of the array, move everything over 1, and then finally update that value that corresponds to the new thing that we have here. In terms of what that would look like as a for loop, we'd actually probably want to start at the end of the array. So that's vector. I didn't use the vector terminology here. Vector length minus 1. I is, because it's going in the opposite direction, I is greater than equal to that location, and then I minus minus. Remember, if you're going upwards, you want plus plus. If you're going backwards, you want your minus minus here. Start at the very end, current end, go to where you're going to wind up inserting something here, and then it would be, give me the values. So vector of I is actually going to be vector of, that's wrong, so give me a second. It's vector dot values of I is equal to vector dot values of I minus 1. And then that last thing would then be, what would be the actual, I don't think this is correct, but it's close enough. Vector dot values of location would be that new value we want to insert there. Feel like I did this slightly wrong, but when we run it, we can at least test it. We got 90% of the way there. Should get some credit for that. That seems to be, oh no, perfectly fine. Why did I even doubt myself for a second here? 0, 1, 2, 3, and the new 3 location is 99, and then everything kind of got moved over by 1. If I wanted to test code like this, I'd really want to make sure, does it work when I want to insert something at location 0? I'm not convinced it'll work when I insert something at location 0, because that's kind of an edge case in terms of how we wrote this code. Yeah, seems okay though. This version of it seems to be working okay. Inserted something at 99, inserting something now with the new location 1, everything just gets moved over by 1. There's one more function I would want us to write. We can start it and not finish it today, which would be if I now want to remove something at location loc. This should be a little bit easier than inserting something, because it's kind of the exact opposite thing that we have to do. For now, what we'll just do, though, is recognize that there would be like a resize operation we want to do at the very end, but otherwise, we would just be copying things back over. Let's leave things here for right now and say, okay, let's say I want to now remove whatever is at location 3. We'll pick this back up on Wednesday and complete this example. But if in the meantime, if you're always at a doubt, okay, do I understand this concept we were talking about today or not? And as you review the video, as you look at structures and pointers, take a look at this example. Fork this code in its current state, and if you can finish that function, you're in very good shape for this. If you look at it and have nowhere to start, well, you'd better come back on Wednesday and we can kind of finish it up together. Okay, otherwise, enjoy. Macro quiz on Wednesday. I know you'll do just fine, but please come.